All right, how's everyone feeling today?
Totally awesome, sir.
All right, wonderful, wonderful. So, ladies and gentlemen, today we're going to be doing lesson 5, which has to do with free fall motion. And basically the question is, how are free fall motion problems solved? So, the truth of the matter is, if you drop an object and it falls through the air, there is going to be air resistance. And the object is going to speed up and speed up and speed up until finally it reaches a terminal velocity. But what I need to point out to you is, if you see that a problem is announced to be a free fall motion problem, then basically we're simplifying the problem and we're saying that the object only has its own weight force acting on it. In other words, we're neglecting air resistance. This is a simplification of reality. The truth of the matter is, on the surface of the Earth, the object would have an air resistance force. But if we're doing a free fall motion problem, we're neglecting air resistance and saying the only force is the weight force. Thus, we know the acceleration would be 9.81 meters per second squared. And the answer to today's question is simply add this piece of information to your list of givens and then treat it like any old motion problem. So the plan is, we're going to first look at a free fall problem more realistically with air resistance. But then we're going to go on and solve free fall problems the way you'll be doing on your homework and on your exams by neglecting air resistance. All right, so here we have a skydiver who steps out of the airplane. Get this out of the way. And when they step out of the airplane, the only force acting on them is the downward weight force, the 600 newtons. The plane is moving forward, but remember, an object in motion stays in motion. So if the skydiver is moving forward, basically they're moving forward because of their own inertia. You don't need a forward force pushing them forward. Yeah. Right. Right. So the only force acting on is this 600 newtons pulling him down. So now the tricky thing is, the skydiver's velocity at that first instant, downward, we're only considering the vertical motion. The downward velocity is 0 meters per second. However, right at that first instant, the acceleration is 9.8 meters per second per second. The only force acting on him is his own weight. But now, something interesting happens. As the skydiver actually starts to fall through the air, the wind pushing up against them actually causes their acceleration to decrease. This is very, very bizarre and complicated because their velocity, you're going to see momentarily, is going to increase, but their acceleration is going to decrease because of the air resistance force. So check this out. It happens kind of quick. Ready? Here he goes. See how they're falling, falling, falling? So finally, as the person falls faster, that upward force here, the air resistance force, increases. And it increases and increases as they fall faster and faster until finally the air resistance force right here, 600 newtons, perfectly matches their weight force of 600 newtons. Now, at this point right here, the skydiver has reached his terminal velocity. It could be anywhere from 100 miles per hour to 120, 130 miles per hour, depending on if they're like tucked in a ball or spread out like a pancake. Remember, 50 meters per second is roughly 100 miles per hour. But notice at this point here, the acceleration is zero. They're not speeding up. They're moving with a constant velocity. Now, check this next business out. The skydiver is going to open the parachute up, and the air drag force, the air resistance, is actually going to increase. Oh. All right. Oh, that's the terminal velocity. That's what we were just saying. Okay, here comes the parachute. Now, once the parachute opens up, for just a brief moment, the acceleration is negative 37 meters per second squared. They slow down at the rate that they're falling from 50 to 30. But once this happens, once again, the air drag force will match the weight force, and the acceleration goes back to zero, and their terminal velocity is 10 meters per second. But now they're traveling a lot slower after they decelerated when the parachute opened up.
So to ride 600 newtons, you need less, you can go slower to provide 600 newtons because greater surface area from the...
Right.
It just never ends.
The two forces balance out again, and now he travels at that slower constant speed, his new terminal velocity. So, at first, he accelerates at 9.8 meters per second squared, but that only truly lasts for a short period of time until he reaches a terminal velocity.
I would think that he would continue accelerating, though.
No, at this point here, his weight force pulling him down is exactly matched by the upward air resistance force. So is this more in law number 2 land or law number 1 land?
Law number one.
Law number 1 land.
Number one.
Law number 1 basically says if the resultant force acting on an object is zero, the object is at rest or is moving uniformly. Law number 2 says if the resultant force is not zero, the object is accelerating. Thomas?
What's causing him to be at terminal velocity, the force pushing up is equal to his weight force. I know how this works in real life and stuff, but in terms of physics and mathematics, how does changing his body posture affect the speed that he's falling at?
You cut the area. More surface area. So
If he gets go faster,
if he's
If-
like this, there's more surface area.
So
more resistance.
If he changes his body and he becomes more of a snow plow, like an air plow, that would increase his upward force. Yes? That would increase his upward force, and that would slow down his terminal velocity. But once it reached a new part, because again, once he starts to slow down, what happens to the air drag force? The slower you go, what happens to the air resistance? In other words, if you're not moving at all, what's the air resistance? Zero. So you spread out like a pancake, you start pushing more air. Immediately when you do that, this force here becomes bigger, yes? And that makes you start to slow down. However, the fact that it makes you slow down, now you're not going to be pushing out as much air because you're traveling slower. So guess what happens to the upward air drag force? It drops back down to 600, and now you go slower at the new terminal velocity. That's kind of like what happened when he opened up the parachute. Okay, you open the parachute. Do you see how that increases the air drag force? Slows his velocity down, and now he's traveling at the new terminal velocity. I don't know, does that answer your question?
Yeah.
Yeah. And once again, the two forces balance out. All right. How many people here, when you become 18, you would like to go skydiving?
I want to go skydiving.
Maybe.
Well,
Maybe not right at 18, but I want to go skydiving.
I personally, I don't think I would do it. You know, I have two children, and with anything like that, there's always a risk. There is a risk. Now, of course, they take everything to minimize that risk, but there always is a risk. I want to show you a video clip of a young man who couldn't wait to be of age and to go skydiving. Okay? Check this out.
Mr. Szynski, everything you do has a risk.
That is true.
You walking right in a car is a risk of you slipping.
Getting in a car.
This is Scott Lutz. Is he a lucky dude or an unlucky dude? Kind of hard to tell. Scott's been waiting 8 years for this. It's his first free fall. Scott and his instructors jump at 12,000 feet. The instructors hold him steady against the rushing wind. Scott is falling fast and loving it. Time to open that chute, Scott. He yanks the cord. The chute opens. Then it breaks away. Yeah, that's right. This freaking chute rips off, and the instructors watch him go bye-bye.
They train you for all kind of different types of chutes. They can be tangled. There can be problems where they're half deployed. And I remember thinking when that happened, I don't think they ever trained me about what would happen if your whole chute disappeared.
Scott plunges to the ground at 125 miles an hour. There's only 1,000 feet between Scott and that.
I deployed the chute. The chute opened, and I looked up, and the chute was full and round, which is a good sign. But the next second, the chute was disappearing. I was going further and further away from it. Thought, I'm going to die.
With only seconds left, Scott can't find his reserve chute open.
I was falling upside down at about 125 miles an hour. One of my instructors was coming down trying to get to me, and they were pointing, and I saw the metal handle, and I grabbed onto it, and I thought, well, this is my last chance. If this doesn't work, then I'm dead.
His reserve chute finally opens. It looks like he's lucked out. Now all Scott has to do is float gently back to Earth. Unless, of course, he's unlucky enough to hit some power lines. Well, there's Scott, and there's the power lines. Guess where Scott's going? Now that's unlucky.
Power lines. They were just everywhere, and I could hear them. They were crackling, and I knew if I hit the pole, I would be grounded, I'd be electrocuted. And I remember thinking at that point, I'm going, I just survived my chute malfunction, and now I'm going to hit power lines. And I thought, what's next? I felt like Wile E. Coyote.
Scott got zapped for third-degree burns on his leg and foot. He needed 2 skin grafts to repair the damage. How does he feel about skydiving now?
I'm never going to jump again. I don't think most people realize how little time you have. If something goes wrong, you just have a matter of seconds between whether what you do will make you live or kill you.
Scott's one of the unluckiest dudes around. Well, yeah, but he's still alive. So I guess that makes him an extremely lucky dude.
Or he's...
Yes.
Do you know if they have I remember I was talking to my cousin once, and he said they went skydiving and they had the parachutes are pressure controlled, so even if you don't pull the thing at a certain pressure.
Yes.
Don't they have that?
Yes. Obviously, he wasn't wearing that, but yeah, I've heard of that. That's true. Yeah.
That's why I'm gonna use skydiving.
All right. So as I was saying, the reality of the situation: if you're falling through the air, actually your acceleration would actually be decreasing to 0 until you reach the terminal velocity. But we're going to simplify these problems. We're going to model them in such a way to say the only force acting on the objects is the weight force, and therefore it's going to be accelerating at 9.81 meters per second squared all the way down. So to solve these problems, you simply add this to your list of givens. Let's take a look at a sample problem.
Is it about Scott?
How far will a rock dropped from rest? How far will a rock, comma, drop from rest, fall in 3 seconds?
Use great displacement formula.
So the first thing we do is try to follow proper problem format. And we realize we have a piece of data here. There's your given. We have time equals 3 seconds. And if they want to know how far, ultimately, we're going to be finding the downward displacement, x. And at first, it seems like that's the only thing that was given, the time, and now we're trying to find the downward displacement. But there are other hidden things. For example, the fact that they're dropped from rest. What can I add to my list of givens, Thomas? Yes, the initial velocity is 0 meters per second. So that wasn't directly stated, but you kind of like inferred by reading the problem. Also, you recognize that it's a free fall motion problem. So, Richie, what else can we add?
Acceleration has to equal 9.81 meters per
Right,
second
and
squared.
since this is an AP course, we could just round it to 10 meters per second squared. Now we're good to go. There's many different ways of solving this problem, but the most direct way is to use the great displacement formula.
But you don't have a final velocity.
You could solve for that final velocity, but you don't need it if you're only looking for the displacement. Here, since the initial velocity is 0, that term's going to go, and you're left with x equals 1/2 times 10 meters per second squared times 3 seconds squared. And what does that come out to? 45 meters?
Yeah.
Of course, this is neglecting air resistance, but you can assume it's a free fall problem, and that's what you're expected to do. Unless you're directly told more information about the air resistance. Let's look at another example.
Is there a separate formula for air resistance?
No, you would have to apply Newton's second law and then find the resultant force and then put it in F net equals ma.
Got it.
And the acceleration wouldn't be constantly 9.81 meters per second squared.
Okay.
So here we go. Another example.
You just like make these up on the spot?
Yep, a ball is thrown upward 40 meters per second. How high will the ball go? Now this is a little bit different because the ball isn't dropping through the air, it's being thrown upward. Now if you throw a ball upward at 40 meters per second, is it going to just keep on going 40 meters per second forever and ever and ever? What's it going to do, Brett?
It's going to accelerate at first, and then it's going to decrease in acceleration and increase velocity. When it goes up, then it will equal, and then it will have a terminal velocity.
Okay, remember, we're neglecting air resistance.
Acceleration will be constant.
Okay, so the acceleration is always going to be the same number all the way up. But since it's going upward, what is its weight force going to do to that speed?
It's going to push it down.
Right. So is the person going to keep going 40 meters per second?
No, it's gonna decrease.
It's going to decrease. So we know now the initial velocity upward is 0 meters per second. But since it's going to be decreasing, what do we write down as our acceleration?
Negative.
Negative 10 meters per second squared. It's still constant, but it's negative because the object's going to be slowing down. Now, interesting enough, the object goes up, slows down, slows down, slows down, slows down, until at that final highest point, it stops. So we could say the final velocity equals 0 meters per second at the top. And finally, we want to know how high it goes. And I heard someone say it, this shouts out the no time formula. Vf squared equals Vi squared plus 2 times A times X. The final velocity on the way up is 0. The initial velocity,
40.
oh, I should have listed that here. Oh, this here should be a 40. That should be a 40 there, sorry. Initial velocity is 40. It's 2 times negative 10 meters per second squared times X. So this is going to be 0 equals, what is that going to be, 1600 plus negative 20x. And then you bring the 20x over to the other side. 20x equals 1600. X equals
80.
80 meters. Now, if you were asked to find the total time up and down, you might want to first just find the time on the way up, and then guess what you could do with that time? Well, if you find the time up, and you want to know the total time, say it took like 5 seconds to go up. So then what would be the total time up and down? Right. So you're going to multiply by 2. I thought you said divide.
No.
Okay. All right. So the bottom line for today's lesson, when you're solving free fall motion problem, you're going to add this acceleration to the list of givens. But sometimes it might be positive, sometimes it might be negative, depending on your reference frame. Yes?
So it's always going to be 10, right?
If you're near the surface of the Earth.
Okay, so it's never going to give us, you're never going to give us a problem where it's going to be on the moon.
If it was on the moon, the problem would state that,
Oh, okay.
and then you would have to take it from there.
It's 1/6, right?
Wait, let's get a little question. Why is the
1/6.
Why is
So-
the acceleration negative in that problem? Because it's it's slowing down.
Because it's slowing down.
I'm left to so you throw it up, and then it goes. So you accelerate stuff, then it accelerates down.
It doesn't accelerate up. It decelerates up.
It has a negative acceleration. It's kind of tricky because if you throw it up and it's going up like this, its velocity is 16 meters per second. Yes?
Yeah.
1 second later, how fast would it be going? Remember, the acceleration is negative 10 meters per second squared, which is negative 10 meters per second. So this tells you how much the velocity is changing by after each second. So 1 second later, if you throw a ball up, it's going to be going faster or slower? So guess how fast it's going to be going? So it would be going 50 meters per second. 1 second later, how fast would it be going? 40 meters per second. 1 second after that, how fast? 30 meters per second. 1 second after that?
20. 10.
1 second after that? 1 second after that?
0. And then back.
1 second after that?
10.
But since it's going down,
Negative
1 second after that?
I see that.
And guess what the acceleration is all the way up and all the way down and even at the top?
0.
No. guess
Oh, I
what the
thought you meant the resultant. I didn't
guess
know.
what the acceleration is? All the way up,
10.
all the way down, even at the top.
10.
Negative 10.
Yeah, sorry, I did the resultant. Right? The resultant would be 0.
The resultant force isn't 0. The resultant force acting on the person or the object
Yeah.
would be the weight of the object.
Oh, right. Yeah, that makes sense.
If the resultant force was 0, then you're back to law number 1,
Right.
and the object is either at rest or in uniform motion.
Gotcha.
Bye, guys.
Mr. Sosinski,
Yes.
my sister goes to New Paltz.